Hi, in this video we're going to look a little bit at what are called one-sided limits. So we're going to start with an example and then we'll get to the definition, the formal definition of what that means. So our example here, we have a graph, and so we don't really have any specific questions about this graph, but one thing you should start to be developing at this point is being able to see the places in this graph where limits would be helpful to help us describe what's going on with the graph. So those would be the places where the function is doing something a little bit unusual. So those places I would say on this graph are at x equals -1. That's a place where the graph is doing something a little different, unusual. Maybe x equals 0, x equals 1, and x equals 2. Those are all places where we might use limits to describe what's going on with this function. And certainly we could consider limits at other places on this graph, but that's really why we use limits, is to describe things when the graph is doing something a little bit unusual. So those are the 4 places where we see something different on this graph. All right, so let's start by thinking about this graph near x equals 0. And so if I want to think about what's going on at this graph near x equals 0, around x equals 0, not at x equals 0, I could consider a limit as x approaches 0 of f of x. And so if we look at the graph of our function, a little bit left of x equals 0 and go toward x equals 0, a little bit right of x equals 0 and go towards 0. And what we'd see is that those two sides of that function, my arrows, my y values, were going to different places. So we would say that this limit does not exist. However, we might be interested in describing what is going on for the graph of that function on either side of x equals 0. So this is where we can use one-sided limits to describe what's going on each side. So I'm going to start out by trying to describe what's happening on the right side of x equals 0. On the right side of x equals 0. So we're going to use limit notation, but we're going to use this extra little symbol to indicate that we are just on the right side of x equals 0. So I'm going to highlight that just so we can kind of focus on that. That little plus right there indicates that we are just on the right side of whatever we're letting x approach. So when we look at the graph of our function and we're just a little bit right of x equals 0 and go toward x equals 0, we can see that those function values are headed toward 0. So the little plus there just indicates that we're looking at numbers slightly bigger than x equals 0. That's what the plus indicates. And then if I want to look on the side of x that is a little bit less than x equals 0, or left of x equals 0, we can use that little minus sign to indicate that. Limit as x approaches 0 from the left of f of x. So on the graph of my function, when I'm a little bit left of x equals 0, I go toward x equals 0, see that those y values are headed toward 1. Now because those two values don't agree, remember that the overall limit does not exist, but what we're talking about now is how we describe kind of the separate limits. Another kind of important thing to pay attention to on this graph, and we've kind of worked on this before, is that these limits are describing what happens when x is close to 0 but not at x equals 0. However, we might also talk about what happens at x equals 0. And remember that when we do that, we're just using function input-output notation. So we would be interested in this graph exactly at x equals 0, and we have a point on this graph exactly at x equals 0 where the y-coordinate is 1. So we just use ordinary function notation to describe that. That's the point 0, 1. All right, let's look at a couple of other one-sided limits for this function here. Let's look another place where we said this graph was maybe a little bit interesting was as x approaches 1. So if I write this, lim x approaches 1 with the little plus up there, that means we're interested in the graph of that function when we're just a little bit bigger than x equals 1, and we want to follow that toward x equals 1 and look at what the y values of that function are headed toward. So it looks like that's headed toward 2. And then if I look at the limit as x approaches 1 from the left, so slightly less than x equals 1, be a little bit left of x equals 1, head toward x equals 1, and look at what the output values of the function are doing, and those are also headed toward 2. So since those two one-sided limits agree, we started this chapter by talking about kind of two-sided limits. The overall limit as x approaches 1 of f of x, that two-sided limit. And so we have these individual one-sided limits and then the overall limit, those all agree. The other thing that we might think about is what actually happens at x equals 1. And you might notice that on the graph of that function that there is no point at x equals 1. There's an open circle at x equals 1, but there's no actual point on the graph at x equals 1. So we would say f of 1 is undefined. All right, let's look at one more here, and then we'll go look at the formal definition. So one of the other places where we said that this function was a little bit interesting to look at was around x equals 2. So we can consider the limit as x approaches 2 from the left. Let's do the left side first here. From the left, so slightly less than x equals 2 on the graph of the curve and go toward x equals 2. You can see that those y values are headed toward 4. The limit as x approaches 2 from the right, so slightly bigger than x equals 2. So that would be on the right side of x equals 2, and I'm going to head toward x equals 2. Those y values appear to be headed toward 1. Since those don't agree, we would say that the overall limit as x approaches 2 of f of x does not exist. We might also be interested in talking about if there's an actual point at x equals 2. So if you look at the graph and you think about what's happening exactly at x equals 2, you might notice that there's no point there. So we would say that that is undefined. There's no output when x is 2. All right, so there's some other videos that do kind of similar thing with just some different graphs, so you can watch those for some more examples. But let's look first at the formal definition. And so I have that typed here. This is just one of them. This is the definition of the limit as x approaches c from the right, a little plus there, from the right of f of x equals L, where L would be a number. Okay, so if we look at this definition, it says for every positive value of epsilon, we can find a positive value of delta, so that whenever the absolute value of x minus c is between 0 and delta, and x is greater than c, we're guaranteed that the absolute value of f of x minus L is less than epsilon. And that's what we mean when we write the limit as x approaches c from the right of f of x is equal to L. So when you compare this with the definition that we looked at before, you might notice that there's just really one important difference here, and that is that we made this restriction that x has to be greater than c. So if you think about kind of the graph, what we meant when we said x approaches c from the right, we're talking about values that are just a little bit bigger than c. So really that is the only difference in this definition from the one we looked at before. And so you can kind of think about that if we were going to define the limit as x approaches c from the left, if I was going to do a similar definition and write the limit as x approaches c from the left of f of x equals L, I would just use the same definition that I have up here above, but instead of restricting x to be greater than c, I would fill in the whole definition, and then I would just change that one part to say x must be less than c. So really the same definition as before, we're just restricting to one side or the other. One other comment I want to make about this definition is that sometimes you'll see this restriction on what x can be written a little bit differently. You can also write that part to say that x has to be between c and c plus delta. That's another way to write that expression, and you can kind of open up that inequality and think about inequalities to rewrite that. I think our textbook actually writes it that way, but I really prefer to just write this definition so it's very, very similar to the one we looked at before, with just the one restriction that should make sense to you. X has to be greater than c for the limit as x approaches c from the right. And then if we want to talk about the limit as x approaches c from the left, the only change you would make is to say that x has to be less than c. All right, so in the next couple videos, it's just some more examples, graphs, one-sided limits from equations, and some more examples like that.